Yo, what's up, super classes? Welcome to another day of notes. I'm sure all of you are excited. Today might be a little bit shorter than the last couple days. We got to deal with writing equations and some stoichiometry stuff. So, most of this stuff should be review for you guys. So let's go ahead and get going here. Alright, so writing equations. So let's just get down and dirty and get into writing them. Alright, so let's start with something like this. Let's say that we have methane gas reacts with oxygen gas to produce carbon dioxide gas liquid water, and heat. So you should be able to go from a word equation, something like this, all the way to what's called a balanced chemical equation. Right? And you can do it in steps, or you can just kind of do it. Alright, so we got methane gas and oxygen gas. These are our reactants, so they're going to go on one side of the equation. Right, to produce, that's my arrow. Carbon dioxide, which is a product. Liquid water, which is a product. And heat, which is a product. Right, so let's go ahead and write this out. So we have methane. We'll use a small g for gas. Plus oxygen, which is also a gas, produces, there's my arrow, carbon dioxide, gas, water, which is liquid, and heat. Okay. So this is what's called actually a word equation. This is a word equation. Now, we can take that word equation and we can go ahead and come up with our chemical formulas and write the chemical equation. Right, now, so methane, you may or may not know what methane is yet. Alright, so methane's an organic, and we'll do organic later on in the year, but the formula for methane is CH4. If you know the phase, you need to include it. So we know the phase is a gas. Formula for oxygen. You need to remember that oxygen is a diatomic, so it's O2. Yes. Goes to carbon dioxide. Okay, so carbon dioxide is CO2. Gas. Water, which is H2O, and it's in liquid phase. And it produces heat. Now, this is the basic form of our chemical equation. We have to go back and balance it. So the number and type of atoms on the left side of the equation, the reactant side, have to equal the number and type of atoms on the right. And we're going to balance by what's called inspection. Right now, you should recognize this type of equation now. Okay, this is combustion. Combustion always produces CO2, water, and it'll release heat. It's exothermic. Right, so we told you, or I told you, when you go to balance these, start with your carbons. Okay, so this carbon is going to all go to this CO2, so we got one here, we got one here. Then work on your hydrogens. I have 4 hydrogens here, I have 2 hydrogens here, so I need to add a coefficient of a 2 to balance that. And then finally we can go ahead and look at our oxygens. So I have 2 oxygens here, 2 oxygens here, so I have 4 oxygens, so I'm going to need a 2 there. Right? So my coefficients are a 1, a 2, a 1, and a 2. So this is my balanced chemical equation. Oops. in reality, did I need to give you this? Right? I didn't really need to give you the products. You should be, if I just gave you, hey, you're reacting CH4 and oxygen, you should be able to come up with these products. Because this is a combustion, you know that it produces CO2 and H2O, and that's just the energy equation. Okay. So let's try another one. Lithium reacts with hydrobromic acid write the balanced chemical equation. Alright, so in this problem, I didn't give you the products, so you don't have any products. But that doesn't mean you can't figure it out. Alright, so this is going to be a reactant, and the hydrobromic acid is also a reactant. So let's start by writing those. Alright, so the symbol for lithium is Li. It is not a diatomic. Hydrobromic acid. Well, hydro tells us that it's binary. So to come up with that, we crisscross hydrogen with bromine. So we would go H, which is +1, Br, which is -1. This comes over here, this comes over here, and we get HBr. So now if we look at that, can we figure out what type of equation this is going to be? Well, I have an element and a compound. This is going to be single replacement. The lithium is going to replace either the hydrogen or the bromine. So the question is, which is it going to replace? Well, we know lithium is +1. It's a group 1. Hydrogen is +1. And bromine is -1. So will lithium go with hydrogen? Not normally. It can because it's an exception, but not normally. So the lithium is going to crisscross with bromine. Right? So I can predict what my products are. So I crisscross lithium and bromine. And what's left? I got this hydrogen sitting here. And remember, hydrogen's a diatomic, so it needs to be a 2. Alright, now let's go back. Do I know any of the phases? Well, I do. Lithium. Okay, we're assuming that this is happening at either room temperature or standard conditions. So at standard conditions or room temperature, either one, lithium's a solid. It's a metal. So that should have an S. HBr, it tells us that it's an acid, so that tells us this is an aqueous. We should write that. Now, this is a salt. Okay, salts are solids at room temperature and standard condition. And then hydrogen is a gas. So you should be able to fill those in. All right, now, the last thing we have to do is we have to make sure that we're balanced. And we're going to balance by inspection. So let's just start counting atoms. I have one lithium here. I have one lithium here. That's good. I have one H here. I have two H's over here. So I'm going to have to add a coefficient. Now that changes things up. Right, so now I have two H's, two BR's, and only one. So I'm going to need a 2 here. Okay, now that changes my lithiums, so I'm going to need a 2 here. So this is my balanced chemical equation. Alright, let's try another one. Nitrous acid reacts with barium carbonate. Write the balanced chemical equation. Okay. So again, I just gave you a reactant. So I gave you our nitrous acid, which is a reactant, and our barium carbonate, which is also a reactant. So let's go ahead and get the chemical formulas of our reactants. So nitrous acid, okay, remember no hydro, so that means this is a polyatomic ion. 8 goes to ic, ite goes to us. So this is 8 goes to ic, ite, so this is nitrite. This is nitrite. So I do H and NO2. So we get HNO2. It's an acid, so it's an aqueous. Plus barium carbonate, Ba, which is +2. Carbonate is CO3, which is -2. Crisscross. And our other one is BaCO3. Now, you probably don't know what form that's in yet, but it's, okay, it's probably going to be a solid. Now, products. You have to recognize that this is an acid and a carbonate. And we said that acids and carbonates react to form water. That's in liquid phase. Oops. Carbon dioxide in gas phase. Okay. And how did we get the salt? Well, remember we said we use the cation of the carbonate and the polyatomic of the acid. This is your anion. And we crisscross those. So we take Ba, which is +2, NO2, which is -1. This comes over here, this comes over here, and we get BaNO2, 2. And again, you probably won't know what that phase is. If you don't know and you leave it blank, that's fine. Okay. Now, last thing we have to do is we have to balance. Alright, let's start with our H's. I have 1 hydrogen on this side. I have 2 hydrogens on that side, so I'm going to put a 2 here. I have 1 nitrogen. Oh, I lied. I have 2 nitrogens, and I have 2 nitrogens. Okay. Oxygen. Let's leave that one for a second because that one's a hard one. I got 1 barium on this side. I got 1 barium on this side. Carbon. My carbon is good. I have 1 carbon and 1 carbon. So let's deal with my oxygen. I have 4 oxygen atoms here and 3 here for a total of 7. Let's see what I got on this side. I have 2 here and I have 1 here. And I have 4 here. 4, 5, 6, 7. So my oxygens are actually balanced also. So this would be my balanced chemical equation. All right, let's do this one. Ethane is burned. Write the balanced equation. All right, so as soon as you see burned, that means it's combustion. This is an organic, and we're going to react it with oxygen. So the formula for ethane is C2H6. We're going to react it with oxygen gas. We know that it produces carbon dioxide gas and H2O liquid. You probably don't know what form that's in, and that's fine. Now, let's go ahead and balance this. So in these combustion reactions, I told you to start with the carbons. Right, so I have one carbon here, or excuse me, two carbons here. I have one on this side, so I'm going to need a 2. Then I said do the hydrogens. We got 6 on this side. We got 2 on this side. So to fix that, I'm going to put a 3 here, and that gives me 6 hydrogens. And then once you've done that, then go ahead and work on your oxygens. Now, I'm going to give you another little hint. Okay, something that you can do. All right, so if you just add up your oxygens, so I have 4, 5, 6, 7. Okay, you can do this. If I have 7 oxygens on this side, I can do 7 halves over here, and technically that balances it. Okay, so you can just count up your oxygens, okay, put that number over 2. I don't want you to have fractions in this though. Alright, so how do we get rid of this 2? Well, we multiply this whole thing by 2. So what would happen if I multiplied this whole thing by 2, I end up with 2 C2H6 plus 7O2 gas goes to 4 CO2 gas plus 6 H2O. It's just a little trick that'll help you balance these equations. Okay, and if you use that trick, this becomes pretty easy. So for example, let's say you have a crazy one that's big. Let's say we have C10H20 and it reacts with oxygen to produce CO2 and H2O. If you use this little trick, this is a lot easier. Again, you still start with your carbons. Alright, so I have 10 carbons here, so I have 10 here. Then we do our hydrogens. I have 20 here. I only have 2 here, so this is a 10 also. Alright, and then you just count your oxygens up. I got 20, I got 30, so I go 30 over 2. Alright, and then I just distribute, again, I multiply this whole thing by 2, so I end up with 2 C10H20 plus 30 O2 goes to 20 CO2 plus 20 H2O. That's just a little shortcut that can help you when you're balancing your combustion reactions. Now, there's one thing that I can't remember if I mentioned it in the video or not, so I'm going to say it here. Synthesis reactions. Okay, so this is when you have 2 or more reactants going to one product. And you know this. These just have another name. These are also called combination reactions. Okay, and this is how the textbook uses this type of reaction. It's called a combination reaction. So you'll see both. I call them synthesis reactions. You will see them named combination reactions also. Right? I can't remember if I said that in the notes on last class, so I just wanted to bring it up here. Okay. So you're going to be doing some writing of equations and homework. The next section that we're going to deal with is we're going to start to get into what's called stoichiometry. So we're going to be using these equations to actually do some math. So once we have these coefficients, this is a set ratio. That ratio is not going to change. So for example, for this one, I will always need 2 lithium atoms, 2 molecules of HBr. It will produce 2 lithium bromide molecules and 1 hydrogen. Alright, So this ratio is a constant, and we can use that ratio for different things. So we can use the coefficients of a balanced chemical equation to calculate moles, mass, or volume of products or reactants. So let's just write this equation. N2 gas plus 3H2 gas produces 2 NH3 gas, okay, ammonia. This is actually called the Haber process, and you'll read about this year, right, making ammonia. Now, there is a coefficient here. We don't write it because it's a 1, but there is a coefficient there. Now what this is telling me is that it can tell me two different things. It can say if I have 1 molecule of N2 and 3 molecules of H2, it will produce 2 molecules of NH3. But in reality, we don't work with molecules, we work with moles. So what this is really saying is 1 mole of NH2 reacts with 3 moles of H2, and it will produce 2 moles of NH3. Okay, so it's a 1 to 3 to 2 ratio. Okay, we can use this ratio to figure out different amounts that are made or used up. Okay, because that ratio is always constant. So for example, okay, let's just say that instead of 1 mole, we had 2 moles of N2. Okay, it's doubled. Well, 2 moles, we would need 6 moles of this, and it would produce 4 moles of NH3. What if I only had a half a mole of N2? Well, I would only need half of this, so I would only need 1.5 moles of H2, and it would only produce 1 mole of NH3. So we can use this ratio, and that's called stoichiometry. Now, there are 2 different ways that you can do this, and I'm going to show you both. Okay, first thing you're always going to do is you're going to write the balanced chemical equation. And then if you do it this way, you're going to set up a chart. And you're going to set up a ratio. And then you're going to solve. And I'm going to take you through that. This is one way to solve stoichiometry problems. There is a second way. We can use dimensional analysis. So when we're using dimensional analysis, we're always going to convert what we have to moles, and then use the ratio to solve. I'm not sure which is easier, and I'm going to actually show you both, and it really doesn't matter which way you do it. Alright, so let's just do it a couple times, and you can kind of figure out what you like to do. So, let's start with a problem. How many grams of H2O liquid will be produced by the combustion of 3.4 moles of ethane gas at STP. Now, okay, let's start by doing it with a chart first. Okay, so what I told you to do is write the balanced equation to start, so that's our first thing. Okay, we actually wrote this equation already. Okay, so it was one of the ones that we did. All right, it's back here. Here it is. Here's our ethane. All right, so let's just copy that down. So we got 2C2H6 gas plus 7O2 gas producing 6H2O liquid and 4 CO2 gas. So there's our balanced equation. The second thing I told you to do was write a chart. Make a chart. Now, this is what I mean by make a chart. And this is going to seem like a lot to start. It's really not. We're going to label this one moles. We'll label this one total mass. It's total mass and volume, and this is for gases only. Okay, this is for gases only. Alright, so let me show you how to fill out the chart. Now, for the mole section, all it is the coefficients. Alright, so this is a 2, this would be a 7, this would be a 6, this is a 4. Now your total mass is coefficient times GFM. Right? It's coefficient times GFM. Right? So for this one, we got carbon, which is 12. So that's 24, that's 30. So the GFM of C2H6 is 30 times 2. This would be 60 grams. Right. Same thing here. We would take 7 times the GFM. Oxygen is 16 times 2 is 32. So we do that, we get 224 grams. All right, this would be 6 times 18, which is 108 grams, and then this is 176 grams. Okay, so remember it's total mass. Now, volume is for gases only, so it's not going to be this one. We can't use that one. If you remember back, 1 mole of a gas at STP has a volume of 22.4 liters. And we can use that ratio or that relationship here. Alright? So for this one, you're going to take 2 times 22.4 liters to give us 44.8 liters. This one is 7 times 22.4, which would be 156.8 liters. That's a liquid, so we can't deal with it. And this one's 89.6 liters. That's how you fill out the whole chart. Now, in reality, you're not going to be filling out the whole chart because we don't need the whole thing. We only need parts of it. So the next thing that I ask you to do is to set up a ratio. Okay. So what I want you to do is I want you to go into the problem, all right, and figure out what you know and what you don't know. So we have 3.4 moles of ethane. That's our known. I want you to put that above the ethane. And we want to know how many grams of H2O liquid. So this is my X in grams. That's important that you include the units because the units tell you which part of the chart you're going to use. Alright, so now we can set up a ratio. These two numbers go on top. Okay. So my 3.4 moles, X in grams. Okay. It's okay that they're not the same unit. Now, the unit tells you which of these to use. So this one is in moles, so I'm going to pick the moles, all right, which is going to be this one. This is in grams, so I have to pick my grams. Okay, so here is my ratio. The top is always from the problem. The bottom is always from the chart. Now we just cross multiply, and X ends up equaling 183.6 grams, which is way too many sig figs. Probably would be 180 grams. Now, let's talk about this. Which part of the chart did I use? I only used this part, and I only used this part.